Before we do this, I want to make a couple of announcements. Joe's going to make an announcement that will help us report bugs, and then even if you want, download the code. So Joe?
Yeah, so if you, we have a GitHub repository for Tetrad in public code. And if to get to it, just go to Google and type GitHub Tetrad. And it'll give you the link right to it. And on that link, if you go to that repository, there's a place where you can submit bug reports or comments. Even if you just have comments, like even if you want to praise us for a wonderful code, you have so much ease in dealing with, you can put that right there.
Good luck with that, Joe. And I also want to make an announcement. I don't have the link here, but Lizzie Silver, you want to just say that?
Yeah. So a lot of people are asking me, oh, where do I find this? Where do I find that? Can we sign up for your mailing list? Where's the list of speakers? So I put it all on a hackpad, which is a collaborative document that anyone can edit. And I'm going to put the link to that right on the board. So you can just go to this one place and click on the link, rather than like trying to type out a URL that's 150 characters long. If it doesn't fit in a tweet,
you're saying convert to this?
That's a principle.
Yeah.
Okay, so the next thing I want to talk about is, now that you've sort of understood what it is to be equivalent, right, what we like is to have some object, some graphical object, that will tell you the equivalence class, right? It will just tell you at a glance, right, what are all the models that are equivalent, and then you can start from there in understanding what it is that you think you know and what it is that you don't. So we have two kinds that I'm going to go over, and there's many others. The first kind corresponds to that deseparation equivalence theorem, and it's called a pattern. And it was also invented by Verma and Pearl, and it's a graphical representation of the deseparation equivalence class among models with no latent common causes, right? And one of our graduate students, Thomas Richardson, generalized an idea that we worked on for many, many years and put together this notion of a partial ancestral graph, which is a graphical representation of a set of equivalent models that are deseparation equivalent over a set of measured variables, but might also include latent variables behind the scenes. We'll go into that tomorrow. Okay, so let's talk about patterns, and let's show you, right, what they are and how to work with them, and then that will be what the search gives you. So when you do a search on data, right, the first and most simplest set of searches are looking not for graphs, but for patterns. And so we're going to have, right, the output of the search be a pattern, and so it's crucial you understand what the pattern is actually telling you. Okay? And in a pattern, unlike a causal graph, there are three kinds of edges. We call the null edge when there's nothing connecting x1 and x2. This is the undirected edge, right, between x1 and x2, and this is a directed edge. So all of those three are possible in a pattern, and in this pattern, right, over here, that has all three possibilities. x1 and x2 have an undirected edge, x1 and x3 have no edge, and these guys have directed edges. Okay? So what do they mean? Well, if I have in a pattern no edge at all between x1 and x2, that means that x1 and x2 are not adjacent in any member of the equivalence class. So if you see in the pattern they're not adjacent, then in all the graphs that pattern represents, neither are they adjacent there. If there's an arrow from x1 to x2, that means that x1 and x2 have that causal relationship in every member of the equivalence class. And as you would expect, if there's an undirected edge, that means we can tell they're adjacent, but we can't tell the direction or the orientation. So in some members of the equivalence class, x1 causes x2, but in other members, x2 causes x1. So what we know is limited, but we know something. Okay, so here's a simple case that represents exactly the case I've been showing you, right? The pattern on the top represents an equivalence class with two members, and the only difference between them is the direction of the x2, x4 connection, okay? So if I give you the pattern on top and I say, what does that represent, you can easily do that. Okay, so take out your pencils and papers, and here's the exercise here, and it's a little trickier than you think, right? So if I give you on the top, right, this pattern, right, and if I give you that, oh, those aren't even, sorry, I've made a mistake. Those are the patterns. Specify all the graphs that are represented by these two patterns. Now, if you can't see that in the way back, right, x1 is the top variable, and x2 is on the right, x3 is on the left, x4 is on the bottom. This edge is undirected, this edge is undirected, these two are directed into x4. Right? In this one, this is undirected, this is undirected, this is into x2, this is into x2, and this is into x5. Okay? So write down all the graphs that these patterns represent, and there's one little tricky feature you'll see. And what you should be attending to is you don't want to write down a graph that you know to be inequivalent, right? So that's what will help you determine the one little trick. Left one, glance up, and I'll go over that first, then you can go and do the right one. Okay, so on the left one, how many graphs are in the equivalence class that pattern represents? 4 graphs? 3? How many vote on 4? How many vote on 3? Looks like the 3s outnumber you. It is 3, and they differ by the directions of these two things, and I believe that one of them induces an unshielded collider, and that's the tricky part, right? So then we have two undirected edges next to each other. You can't just orient each of them in every way, because in some orientations they both point in, and that will create an unshielded collider, and that's not a member of the equivalent. That's the trick. Thank you for falling for it. You helped me. Okay, so those are the 3 graphs. And now I've done something interesting, which is very handy in Tetrad, is I've marked in yellow, right, the edges that are, in some sense, right, not oriented by the pattern and arbitrarily chosen in the actual members of the equivalence class. Yes?
This is just a quick question about Tetrad. Are you able to export JPEGs or do you screenshot these?
I don't remember. We can export JPEGs. You can say, you can say create a, I'll show you that in a minute. Yes, you can do that. Yeah.
But you didn't say specify only equivalent column, right? You say columns.
This is specify all the causal graphs represented by the pattern.
So that means equivalent?
Yes. So when the pattern is a representation of an equivalence class, right? So the rule I didn't give you, right, is when you have, right, 2 undirected edges adjacent to each other, next to each other, right, the variable that connects them, right, has to be designated as to be a non-collider. So there's an extra mark, as it were, that we don't represent, but that you have to know about. So I've not really done it in precision, right, but that's the idea. Okay, so in the second one, right, how many members of the equivalence class are there? 3, right? It's the same idea, right? And there it is. All the 3 blue arrows, right, are going to be present in every member of the equivalence class, and because, we have 2 undirected ones next to each other, they actually disambiguate into 3 different kinds, right? And I've missed, that should be yellow, not blue. Okay, now there's a handy thing that I'll just show you but not ask you to do anything about in Tetrad. which is that you can generate from any graph. So if I take this graph here, right, and I say, well, what's the pattern that would contain that graph as a member of the equivalence class, right? I can click on this graph manipulation button, put the graph into it, double click on that and say, right, among the pull down menu, right, generate the pattern from the DAG. And so it does. So there's my graph, and there's the pattern. So in that pattern, all the edges are undirected, right? So anytime you put a graph in and you want to see the pattern, right, which is in some sense characterizing all the graphs that are equivalent to that particular graph, then you can do it. So if you're curious, for example, if you have a hypothesis about a domain and you put it down into a graph, and you want to ask yourself, well, gee, okay, that's a good hypothesis. What are all the other graphs that would lead to the same predictions? You can do that with generate the pattern. That's the idea, right? Okay? Now, I've switched up the order of things a little bit. I was going to really give you a sort of a theoretical talk about search. I'm going to do things backwards. We're going to actually get diving in and do it, and then I'm going to back up after you've done it and give you some theory, okay? So let me demo very quickly what it is to do search, and then I'm going to have you guys get into it. Okay. Okay, so yesterday, right, I showed you these equivalent models, and I had you estimate today in the same sort of spirit, whereas in this one, right, we had the graph that looks like that, and then I did a one-edge difference here to change out of the equivalence class to remove the unshielded, to stay in the equivalence class, and here I switched this graph, this edge, so I went outside of the equivalence class, and I showed you how those ramify in terms of the estimator. So now I want to go and move the other way and do search. Okay, so we have this data, and the data set contains only the variables in the data, and there's no information that is carried into that data set that tells the program or us from whence it came, what model it came from. It's just a data set. So I could save it to the workbench, start a new session, import the data, and it would just be data. But I can tell what graph and parametric model generated that data, so this is going to be a handy example. Okay, so if I want to search, I click on the search node, I put it on the workbench, and I put the data into it. Right? And I'm going to go in a few minutes and show you how to add background knowledge that will constrain the search, so it's only going to look for, right, equivalence classes, right, or members of the equivalence class that are consistent with your background knowledge. So, that's perfectly sensible. In a lot of cases, you know time order, you have plausible theories about some of the relationships, but not others. You ought to be able to enter that and constrain the search to only look for models that you consider plausible. But in this case, I'm not going to do any of that. I'm just going to search. So when you double click on the search, you get this bewildering array of options. Right? There's a lot of different search algorithms. The first set of them are all called pattern searches. Right? Every one of those algorithms essentially starts with data, right, and searches for this pattern thing that we've been talking about. Right? It does it in several different ways. The two that are the sort of the simplest are the PC algorithm, which is, right, searching with using independence constraints that it tests for sequentially and then narrows the graph space and the pattern space. And then the other way is, the simplest is the FGS, which is called the fast greedy equivalence search. And that really does a score-based search in which we look for the whole pattern, right, and calculate its score. And then if it's not, right, the best pattern we could do, we look for a different pattern that might have a better score. Yeah?
When you say fast greedy, is it similar to like the greedy algorithms using motif selection, or is this your own?
Using, sorry, what?
Used in motif selection and discovery, or is this like your own proprietary algorithm?
This was this is an improvement on what was called the greedy equivalence search that was invented by Max Chickering and Chris Meek and Dan Geiger, I think. back in when, 1990 something? 1995 maybe. So the idea is basically to say, if I give you a pattern, what I will know is that every member of that pattern's equivalence class will have the same score on the p-value or on the BIC or on the whatever the measure is, because it's going to have the same fit and it's going to have the same complexity. So then, to search the space, right, turns out to be very, very important to do it efficiently because it's so easy to search into a local maxima. So the greedy equivalence, right, search is a way to search from one pattern and do a one-edge flip to go to a different pattern, right? It doesn't consider one-edge flips that keep you in the same pattern because that wouldn't help. They have the same score. So the fast greedy equivalence search is what Joe's done to modify that. So instead of searching for only 30 or 40 variables, which we were limited to about 15 years ago, we can now do up to 1 million. So there is no set of variables, I think, that you could measure that we can't search, as long as the graph underlying it is reasonably sparse. So that's another topic we'll get to later. But if I choose the FGS and I say OK, right, I'm put in this box, and I have a few parameters I can actually modify. One is the penalty discount. One is the number of patterns, and one is the depth. I'm not going to go into those at all, but we can talk about that more later. But to execute, I just click on execute, and then I get this thing. Now here's something I'll show you that's really handy. If I go to the graph, and I want to compare the graph to the output, I can right-click inside there and get this layout button, and then say copy layout. And then go into the place I want to deposit that layout and say paste layout. And it pops it into the same thing. And now you can see, right, that what it's found as a pattern, right, is exactly the right pattern, which is not necessarily the case because it has to make statistical decisions, right, that are accurate. But this is a sample size of 1,000, and so that wasn't too problematic. Okay? So that's the pattern that actually emerged. Now, if I say, okay, let's see if I've gotten a pattern that fits the data, because it doesn't necessarily mean that pattern will have a good model fit, right? Because I still want to be able to test to see if that model, right? Because there might be no model that fits your data. That's quite common. It's very frustrating. So how do I do that? Well, if I put an estimator, right, and I put data into it, and then I say, okay, take the results of the search, that pattern, and try to estimate it, it won't do it. Why? Because you can't estimate a pattern, you can estimate a graph. So you have to first take that pattern and from it pick arbitrarily somebody, some graph that's in the equivalence class of that pattern. And luckily with this graph manipulation box, you can do that. So I'm going to put that onto the workbench. I'm going to put the search into that, and then when I click on this, right, it has many options, and one of them is, right, to choose a DAG in the pattern. And that's what I want to actually select. So I'm getting a pattern from the search, and now this is going to choose from that pattern one of the guys. And what it produces, you can see, right, is a graph with the arrow from X2 to X4 colored in yellow. What that tells you is that arrow direction is arbitrary. There's nothing that the data will tell you about that arrow direction. So you shouldn't take it seriously when you do your scientific conclusions. The blue arrows were favored by the data. They mean something causally. The yellow arrows mean nothing causally. They're just placeholders to show us some choice we've made so we can get some way to estimate these models. Okay? So this is, I think, the best interface piece we've done because it really helps you understand what the data are capable of telling you and what they're not. Yeah?
Is there anything to do with the thickness of the line? Is there any properties that give us any indication about this output, or is it just?
Yeah, I'm gonna show you that now. So if I estimate now this model, right?
Could you repeat the last bit?
Sure. So the data, right, I search, and the search is not searching for a graph, it's searching for a pattern. So then I can't estimate the parameters in a pattern. So I can estimate the parameters in one of the graphs that the pattern represents. They're all equivalent, but I just choose one. And the program with this graph manipulation button will do that for me, right? Which is very handy, right? I could choose a different pattern, but it chose this one. It oriented the x2, x4 edge this way. It could have done it the other way. But it shows me that edge in yellow to tell me that that edge is oriented arbitrarily as a random choice, and it could do it the other way, and it'd be just as good. It would be the same, it would be in the same equivalence class. So that's telling you, right, the blue arrows, right, there's evidence from the data to point and orient them. And the yellow arrows, there's no evidence from the data whatsoever. They're arbitrary and should not be taken as meaning anything causally, right? They're just placeholders. So that's going to help you determine. I mean, it's not like we know that X1 truly is the cause of X3. We don't know that, but there's real evidence from the data that tells us, you know, that's maybe likely.
So all the algorithms will give you the same results?
No. In many cases, they'll give you slightly different results, right? And I'll get to that in a few minutes. But I think the basic algorithms in basic cases like this will all give you the same results. And I'll check that in a minute. But just to finish this picture, right, I get this as my graph, and if I close that, I still can't estimate this because it's not a parametric model. So now I can parameterize that graph as a structural equation model, and it keeps that arrow in yellow to keep reminding me that it's not anything that I should take seriously. And now I get the estimator. And again, so this is your final object. So this is exactly what I think what you were asking me. And now I get the parameter estimates, and what you're seeing is that the arrow from x1 to x3, which is in blue, has an estimate of 0.4786, and it means something causally. Because it's in blue, that means the data tells you that there's some evidence for that arrow. The yellow arrow has a parameter estimate of 0.6978. It means nothing causally. So just ignore it, right? Anything that's in yellow, you can't tell the direction, so you can't actually make any decisions about what's going to happen in an intervention based on that decision. Okay? Okay. So let me just give you one more piece and I'll set you loose, right? If I do another search, right, and I say this time do the PC algorithm, I get a different set of parameters. I get an alpha value and a depth, and the alpha value corresponds to the p-value that will determine whether that particular independence relationship is judged to be significant or insignificant, right? So what I'm doing in the null hypothesis for that test is I'm saying the null hypothesis is independence. And then the p-value says what level I'm going to reject independence. So if I take it from 0.05 and I move it down to 0.01, I'm making it harder to reject independence. And so I'm going to keep independence more often, right, which means fewer edges. The problem with this algorithm is we don't have a theory, right, that tells us exactly what this alpha level should be in all cases at all sample sizes. We know that 0.05, right, is something that is a reasonable default in medium-sized samples, but as the sample size increases, one has to drop the p-value successively at a certain rate, so we have asymptotically, right, the consistent results we actually can prove, but nobody quite knows that rate, and it's very complicated and it's very hard to express exactly. We've done lots of simulations, right, and so we can give you some guidance about that, but unfortunately there is no theoretical answer that we can provide about what that p-value should be. But what you can see is if I do the search at the p-value of 0.05, right, I'll get the same result I just got. But if I change that to something like 0.5 and then execute it again, well, that won't change it. But then if I put it to 0.9, I get different results. So you can change the results that you get the output depending on what judgments the program is going to make about independence. Okay? And that's a very complicated picture that I don't really feel comfortable. There's lots of work on how to actually get around that. We can point you to all of it, right? But it's something you should know about. The default 0.05 works perfectly well for medium-sized samples, and by that I mean things about 100 to 1,000, that kind of sample size. Okay? Yeah?
What's the difference between the solid line and dotted line?
Dotted line?
Yeah.
there should be no dotted lines. Oh, no, that's just graphical. It's an undirected line. There's no dotted line. It just looks that way from the low resolution. Okay, so why don't you guys, it's now 10:15, so let me also show you one more thing, and then I'm going to set you loose, right? And you can play with the searches on the estimate one that you actually did yesterday, and I'm also going to show you the charitable giving example, so you can play with that as well. Yeah?
So, are there any good starting values for FGS, just as 0.05 in PC?
FGS doesn't use a significance level.
Yeah, but it has a different set. What does depth versus length equal one?
So in the so the depth in the PC algorithm refers to the size of the conditioning set, right, that one's going to go to when you actually analyze what independence relations one has to do. Now it turns out that the bigger the graph, right, and the more edges that are in it, the more independence relations one has to check, right, to actually find out what's what. And if I have two variables, x and y, and there's 45 other variables in the system, right, I could condition x and y on just one variable, 45 different ways, or two variables, 45 choose two different ways, or 45 choose three, et cetera, et cetera, et cetera. And the depth refers to how many, right, Joe? It's how many variables in the conditioning set, after which I'm going to say, don't condition on 45 other guys, right? That's too many, you lose power with everybody you put in the conditioning set. And so we can constrain how big that conditioning set goes, and the output is still consistent. It's still informative. It might not be as informative as if we were conditioning everybody, but there's a balancing act there too. So if you have large data sets, right, the depth is important to constrain.
-1 is no constraint?
-1 is no constraint at all. That's the default. On the FGS search, the main parameter is the penalty discount. So if you have any familiarity with all the scores that apply to model selection, right, BIC, AIC, right, minimum description length, etc., they all do something similar, which is they look at two numbers, right, to give you an overall score of the model. The first number is how closely, right, we're able to fit the data in the sense of the prediction we're making and the actual observation, right? It's never going to be perfect, right? As I showed you before, you have degrees of constraint, but it can be closer or farther away. So there's one number that measures how closely, right, your prediction is getting to the actual data. And then the second number, right, is a penalty for how complicated the model is. Because if the model is very complicated, it's pretty easy to get close to the data. And if the model is very simple, it's very constrained and it's very hard to get close to the data. So you have a discount for the complexity of the model, right? And that discount, right, is computed differently for different scores, right? And you can, as a user, you can set the discount, right, up or down, depending upon whether the model you're looking at is ridiculously complicated and you want to simplify it, right, and pull out all the edges that are actually robust, or, right, if you want to make it the other way because there's no edges coming out and you want to add more edges. Yeah, Joe.
I just want to point out that this is for continuous data. All the variables are continuous. If you have all discrete data, then it uses a BDU score, which has a sample prior and a structure component.
Right. Whole different topic. But the idea of the penalty discount, right, is allowing you to, it's the analog in some sense, right, of the alpha level and the other one. You can make the models more and more or less sparse. So
The discount goes higher, will it make the graph sparser or the other way around?
the more you penalize complexity, the more sparse it'll be. Right, in this case, I'm not getting. Yeah, eventually, if I made it, I'll penalize complexity so much, I'll just choose the simplest graph. Right. So if I go all the way down to almost zero, it puts every edge in there. So I think the theoretical value for this, Joe, is 1, right?
I put 4.
But the theoretical value is 1. Right. So the theoretical value is 1, and that governs what this score should look like asymptotically as the size of the sample grows without bound. Right. All these things, right, work beautifully, right, when the sample is enormous and the assumptions are satisfied. Right. It's all beautiful, and the theory is just what you'd expect. But when the sample size is small and some of the assumptions are not satisfied, it's a little bit of an art and a little bit of a science. Okay, so let me just show you one more topic before I set you loose, and then you can go ahead. So this is background knowledge. Now, suppose I have the following graph, right? X1 is caused by X3, X3 causes X2, 2 causes 4, and 4 causes 5. So you now know enough that if I said to you, if I did a search for this graph and the data are representative and I do all the right statistical decisions, what pattern am I going to get if I do a search from data generated by this graph?
Not going to have any directed edges.
I will have no directions in the edges. It'll be the undirected skeleton that'll have the same adjacencies as this guy. So let's make sure that's true. So here's my data, here's a search, right, and that's what I get. Okay? Now, the way to build background knowledge is to put one of these knowledge boxes on the table. You click on this guy, you put that in the table, and then you drag from the graph into the knowledge, and that just tells you what variables you're going to be dealing with. And then you open the knowledge box, and there's several different things you can do, but tiers and edges are the simplest. What you can then do is you can put tiers of the variables together which carry time order information. And the basic idea is that anybody from a later tier is prohibited from causing anybody in an earlier tier. But everything else is allowed. Right? So if I put something in place like I did here, right, there's nothing in the time order. Here, right, I've put 1 and 3 in tier 1, and I've put 2, 5, and 4 in tier 2. So that doesn't say anything about whether 1 causes 5, 2, or 4. It just says that if you're in tier 2, you are not allowed to cause tier 1, right, because you're later in temporal or causal order. So it constrains it in some degree, but not entirely. Okay, so if I do that, now in the first one, right, I didn't do anything in the tiers, but I can require certain edges and I can forbid certain edges. So you might have a very particular, right, set of variables. In some of the variables you might say, I'm going to require this edge. For example, in the lead and IQ example, right, one of the variables is parent's IQ and one of the variables is the child's IQ. Right? You might want to require a causal edge from the parent's IQ to the child's IQ because we know that, right, happens genetically and we know it happens environmentally. So, right, I think it's safe to say that the parent's IQ, right, has a direct causal influence on the child's IQ. Right? In this case, I have required that X3 cause X1. And if I say execute, now the search produces a graph in which 3 causes 1, which is interesting, right? Nothing else is oriented, so my requirement of that 3 causes 1 had a very small and very local effect. But now let's go to the other situation in which I made these 2 tiers, and that can be represented by a set of prohibited edges. But the tiers are this way, so 1 and 3 are in the first tier. If I execute that way, right, I get this. Now here's the interesting question. What orientations in this graph, right, came from the background knowledge? And what came from consequences that are more indirect of the background knowledge? So the 1 and 3 were in the first tier, and 2, 4, and 5 were in the second tier. So if I look at the edge from X3 to X2, that's a consequence of my tier background knowledge. Because there's an adjacency, but I've said X2 is in a later tier than X3. It's not allowed to cause it. So the only possibility left is that X3 causes X2. So I can orient that edge, right? Now, what about the X2, X4 connection? Is that produced by the background knowledge directly? No, because X2 and X4 are in the same tier. So why did I get to orient that edge? That's correct. So if I look at the if I look at the fact that X3 and X2 got oriented, and I had another undirected adjacency here, right, which seems to indicate that I can go oriented either way, right, I'm going to be subject to the same problem that you were before. If I oriented X4 this way, right, I will produce an unshielded collider, and that's, right, not what the output said. So even though there's no background information directly that orients this, right, because this got oriented from background knowledge, right, this had to be oriented this way. And then the same thing ramifies down here, right, because now this is oriented. And so you get this domino effect. And that's the beauty of this, all right. In many, many cases, you can make very, very small background knowledge assumptions which can have huge effects in terms of orientation, which is always very satisfying. Right? You want to only put the background knowledge in place of what you really think you know, right, and then let the program go to work. Okay, so that's just up to you. That's your background knowledge, right? So okay, so let me go to the charitable giving case, and I'll show you, right, what I think the background knowledge tells us, and then you can go to work on actually doing it. Okay, so the data I showed you in the charity case was this, right? We built a graph, right, based on theory, and then we got a parametric model, and we estimated it, and it came up, that model had terrible, terrible fit. So now if somebody asked me yesterday, okay, now what do we do? And now you know the answer, right? Now you do a search from that data and background knowledge, and you see what you get. So what's the background knowledge that we should put in for the charity case? Well, right, what do we know about the charity variables? We know that the tangibility condition was an experimentally randomized, assigned to treatment or control condition. So how does that translate into background knowledge?
It's not going to have any errors going into it.
Right, so how would you put that in? It's what's called exogenous. It's absolutely only a cause, if anything. It cannot be an effect because I've randomized it and there's nothing else in that system that could cause it. So how could I code that in background knowledge? I could put that in tier 1 and everybody else in later tiers. That's how I do it. So that's how you code. You have an experimental intervention. So what I did here in the background knowledge, right, was I built a tier where tangibility conditions in the first tier and everybody else is in the second tier, which means anything else goes, but tangibility condition is exogenous. Okay? And that has a huge impact, obviously. Now, so I'm not going to tell you the rest of it, and I'm going to let you play with it. But now, you have enough knowledge to go ahead, go back to the estimation 1, right, do the search I did, right, play around with it, and then go to the charity case, right, enter the background knowledge, and then actually go ahead and see what you find. And there's one more piece of background knowledge or two more pieces I'll tell you. So I did this, that's in the slides. This is the charity case. Here are the 3 pieces, right, of background knowledge that you can use, because the authors in the study tell me this is so. The first 2 I think are uncontroversial. The third one is quite controversial. So the first one is tangibility is exogenous. Clearly they randomize it and that perfectly makes sense. The second one is that the amount donated is endogenous only, which is to say that they did everything else, right, before they asked the subjects what they wanted to donate. Right? So the assumption is that everything else had been already measured and already taken place and was already a property of the person or a property of the condition or the experiment before they asked them, well, how much do you want to actually give? Now, it would be perfectly reasonable, right, for this to be violated, because you might imagine a situation in which, right, I had already decided in my mind what I'm going to donate. Suppose I say, I'm donating nothing. And then they ask me my level of sympathy. And I say, oh, I'm going to donate nothing. So I'm going to write down I have very little sympathy. And then they ask me the impact I think I'm going to have. And I said, oh, I'm going to donate nothing, so I'm going to write down I'm going to have very low impact. So my thought of what to donate could influence the other things, and so this assumption might not be reasonable. The actual measurement of donation takes place after the measurement of everything else. But this is the assumption they made. And then the third thing, right, is a much more controversial, that the tangibility experimental yes or no condition was required to have a direct influence on imaginability. So you're going to have to figure out how to put that in if you want to put that in. Okay? So go ahead and do these searches, and we're going to go ahead and help you. Feel free to take a break and then come back and do the searches, and we'll take at least a half hour, right, to have you play with these searches, because this is now when you really get to actually play with them. If the examples that we've put together are easy and you've gotten them and you understand them, and generate your own examples and apply the search and see what happens, right? Do whatever you feel like will help you get this, but now it's playtime.